second day of our seminar. And the speaker is Osamu Iyama. He's going to talk about the periodic trivial extension algebras and fractionally Calabi-Yau algebra. And please go ahead, Professor.
Okay, yes. Thank you very much again for inviting me this great seminar. And today I will talk a bit different subject from yesterday, but this is also good application of theory of singularity category. Yeah, so I will talk about today periodic trivial extension algebra and fractionally Calabi-Yau algebra. Yeah. And this is joint work with Aaron Chan, Eric Darpo, and René Martin-Tick, and it will appear soon in journal Essence, yes. So French journal. Long name, but abbreviation is Essence, whatever. Yes. So, yes, let me explain the setting of my talk today. So, yes, again, yes, I talk about finite dimensional algebra over field. So K algebra. And yes, K is a field. And just for simplicity reason, I assume K is algebraically closed. Yes. So K equal K bar. This is not the essential assumption, but just for simplicity. And then the main object of today's talk is the so-called syzygy functor, which is denoted as omega, or more precisely speaking, omega A. Yes. And yes, this is a functor from the stable category of A to itself. And it is defined by taking projective cover of module X. So if we have a module X, then take projective cover. Well, yeah. Or surjection from projective module is enough, in fact. And just take the kernel of this surjection. Then this kernel is denoted as omega X, and this is called as the syzygy of X. So this correspondence, sending X to omega X, actually gives a functor not in full module category. Instead, by factoring out a projective module, then this omega becomes a functor from stable category of A to itself. And today I will talk about basically periodicity of this functor. Yeah, basically. But yes, actually what we discuss is a stronger version of periodicity of this functor omega. And to explain it, we need so-called enveloping algebra of A. Yeah, it I think already appeared in Hanihara-kun's talk yesterday. So enveloping algebra of A is just a tensor product of A and its opposite algebra. And yes, considering, so this is enveloping algebra. And considering module over enveloping algebra is precisely considering a bimodule such that the scalar acts centrally. Yeah. So now I can define what is periodic algebra I discussed today. So we call A periodic if the following property is satisfied. And now consider the syzygy of A as a module over enveloping algebra. Yes. So A is of course naturally a bimodule, and the action of scalar is left-right symmetric. So A is module over enveloping algebra. And now consider the syzygy of A as AE module. Yes. And our condition or periodicity is defined by thinking about iterated syzygy or nth syzygy. Yes. So nth syzygy is, well, so thinking about nth syzygy is just to take projective resolution and consider the kernel appearing in here. Yes, kernel appearing here. Yes. and considering nth syzygy of A as AE module, then it is isomorphic to A as AE module. Yes. So there exists some positive integer n such that nth syzygy of A is isomorphic to A as AE. So this is a definition of A algebra A to be periodic. Yes. And yes, there are many many important algebra are known to be periodic. And yes, I will give some example later. Yeah. And maybe just I explain some terminology which will be used later. So the first thing I need is the period A. Yes, period A is n satisfying this condition. Yes, but if I write as period, then we choose n which is minimal integer, positive integer satisfying this property. Yes, so yeah, so period is n if n is minimal with respect to this property. Okay. And actually, yes, there are many examples, just to explain this, I should first remark that there are many possible variations of this property, periodicity property. Yeah. And I explain it as a fact. Yes. So first, possible variation of this periodicity is as follows. So first property is a functorial periodicity or periodicity of syzygy functor. Namely, there exists a positive integer n such that nth syzygy functor is isomorphic to the identity functor as end functor of mod by a stable category. Yes. This is the first possible variation. And the second possible variation is there exists again positive integer n such that, maybe I should write such that here, such that for any x, a module x, and yes, I assume that this is indecomposable and non-projective. Yes. The following isomorphism holds. Namely, nth syzygy of x is isomorphic to x as a module. Yeah, because, yes, I define syzygy as a kernel of projective cover. So if this property, this isomorphism holds, then x cannot be projective. Yeah, because the syzygy of projective module is 0. Yes, but this second condition means if x is indecomposable, which is non-projective, then this condition is satisfied. Yes. So this object-wise periodicity is a second possible variation of our periodicity. And the third possible variation is somehow simplest or somehow weakest, but it's still very strong. Yes. The condition is that, yes. So just restrict the second condition to all simple A modules. Namely, for any S which is simple as A module, we have the isomorphism written above. Namely, nth syzygy of S is isomorphic to S as N. So these three are immediate variation of our periodic property, and there exists the following implication. Namely, first, yes, our periodicity, yes. So A is periodic, sorry, O is missing. So A is periodic algebra, then it implies functorial periodicity. Yeah. So this is easy because nth syzygy functor is isomorphic to the tensor functor with nth syzygy of A bimodule. Yes. syzygy of A as AE by. We have such functorial isomorphism on stable category. So our periodicity implies first periodicity. And the first periodicity obviously implies second periodicity because, yes, just evaluating X, we have such an isomorphism. And obviously, the second periodicity implies third periodicity for simples. So this is immediate consequence from definition. And actually, as I said before, the third simple periodicity actually is sufficiently strong in the sense that 3 implies twisted version of our periodicity. Yeah. So let me explain this. Yes, we call a twisted periodic. So this is yes, weaker version of periodicity. If there exists some algebra automorphism, phi. So phi is K algebra automorphism of A. Yes, such that nth syzygy of A as AE bimodule, it is isomorphic to twisted bimodule A. Yes. So I denote it as 1A phi. Yes. So 1A phi is yes, as a set, this is just A, and as a left A module, it is action. Left A action is usual action, but right action by A is twisted by our automorphism phi. Yes, and such an A bimodule is usually written as 1A phi, and yes, the condition is nth syzygy of A as a E module is isomorphic to this twisted bimodule. Yes. So if this condition is satisfied, then A is called twisted periodic algebra. Yeah. So to avoid any confusion, probably it will be better to write, yes, A is periodic algebra, not module. Yes. And now I just defined twisted periodic algebra by using algebra automorphism. Yes. Then, yes, then this twisted version of also obviously have its variation. So for example, twisted version of the condition 1 I explained before is there exists again K algebra automorphism and such that nth syzygy of nth syzygy functor is isomorphic to phi star. Yes. So this is just induced automorphism of module category given by phi. Yeah. Phi star is just induced automorphism. Yeah. And also we have object-wise periodicity, twisted version of object-wise periodicity. It is also defined by, yes, there exists again algebra automorphism phi, such that nth syzygy of X is isomorphic to the twisted module, module X, but yes, the A action is twisted by phi. Yes. So such a twisted module is also written as X phi by using index phi. Yes. And the third condition is also, yes, very simple. Yes. So, yes. Yeah. So there exists phi satisfying same condition for symbols. Yes. So there is their natural twisted version. Then, yes, first remark is that, yes, actually, yes, the simple periodicity, the third condition is sufficiently strong because, yes, it is actually equivalent to twisted periodicity. So algebra A is twisted periodic. So yes, so this equivalence is actually due to, yes, Green, Snasher, and Solberg. Yes. And yes, and in particular, thanks to this equivalence, all other twisted periodicity are equivalent. Yes. So twisted periodicity, yes. So because, yes, actually third condition and third prime condition are equivalent because there are only finitely many simple module and algebra automorphism just acts as permutation on this finite set of simples. So 3 and 3 prime are equivalent and yes, therefore all other twisted conditions are equivalent. So 1 prime, 2 prime, and 3 prime, all of them are equivalent. Yes. So yes, actually there are not many variation on twisted side. So all conditions for twisted side are equivalent. Yes. But actually periodicity is stronger. Yes, periodicity is still stronger than other twisted periodicity. And one of remark or one of another fact I should state here is that twisted periodicity implies that algebra A is self-injective. So A is injective as A module. So yes, so in this sense, any kind of periodicity condition is a condition for self-injective algebra. So yes, this is just remark. Okay, so now it is time to give some example of periodic algebra. And to explain this, I need to introduce main object, another main object of my talk today. It is so-called trivial extension algebra. Yeah. So if we have a finite dimensional algebra A, then we can define a new algebra which is larger than A as follows. Yes. So TA is algebra as a vector space. It is just a direct sum of A and K dual of A. So D is just a K dual. Yes. And this is a trivial extension. So yes. So maybe I should explain multiplication. So if we have two objects, element AF and BG, then the products are defined by, so yes, degree zero part is actually A is degree zero part and DA can be regarded as degree one part. And yes, A degree zero part is a ring, so just multiply. So A and B are just multiply. Then degree one part is given by AG plus FB. Yes. So in this way, TA has a structure of Z-graded K algebra, and more strongly, actually TA is self-injective algebra. Or more strongly, this is actually a symmetric algebra. So symmetric algebra, so yes, if we say B is symmetric algebra, if an K algebra B is symmetric, then this just means B is isomorphic to its dual as bimodule. BE module. So this isomorphism is the definition of symmetric algebra, and probably yes, it is very natural to expect that trivial extension algebra is symmetric because taking K dual, dA becomes A and A becomes dA. Yes. So yes, at least as a vector space, TA is naturally isomorphic to its K dual. And actually, this natural isomorphism is an isomorphism of enveloping module over enveloping algebra of TA module. Yes. Therefore, yes, trivial extension is symmetric. Yeah. Anyway, yes. So now, yes, it's time to give example of periodic algebra. So yes, now I denote by Q the Dinkin quiver. Then, yes, it is a classical result due to Brenner, Butler, King, in this early this century. It is in 2002 that, yes, first consider path algebra of thinking quiver Q. Yes, but this is not self-injective. Yeah, it has a global dimension 1. So now consider its trivial extension algebra. Then we have symmetric algebra, and actually this is periodic. This algebra is periodic. And moreover, one can describe its period explicitly. Period of trivial extension algebra of thinking quiver is actually either h-1 or twice of h-1. Here, h is so-called Coxeter number. Yeah. It is just the order of the Coxeter element in the while group. Yeah. Anyway, there is some nice formula, and yes, these two cases are divided by the properties that if the canonical involution of thinking quiver is identity or not. Yeah. But yes, anyway, there are two cases. These two cases are explicitly determined by their thinking type. Yes. So this is the first classical example of trivial extension algebra. And yes, there are many. For example, preprojective algebra of thinking quiver is also periodic. And the period is divisor of 6. So 6th syzygy is identity. No, 6th syzygy of A as AE by module, where A is preprojective algebra of thinking type, is isomorphic to pi. Yeah. Anyway, yeah. Preprojective algebra is such example. And a result by Alex Dugas is claims that if A is a representation finite algebra, in the sense that there are only finitely many indecomposable module up to isomorphism, and moreover, if we assume it is self-injective, then this algebra have to be periodic. So all, yes, so self-injective algebra, which is representation finite, are periodic. And there are also deep study by Eldman and Skolonsky. Yes, actually, yes. I think, yes, Eldman and Skolonsky introduced this notion of periodicity. Yes. And they proved that, yes, they gave many examples of representation time. So representation time is the next class of representation finite algebra, and they gave many examples of representation time self-injective algebras. Yeah. Not all representation time self-injective algebras are periodic, but they gave many examples. Yeah. So there are many knowns. So now I want to state aim or goal of my talk. So in this talk, we will give criterions for periodicity, or more generally, twisted periodicity for trivial extension algebra of certain finite dimensional algebra. And also give or construct examples of periodic or twisted periodic trivial extension algebras. And in particular, as an application, we study a well-known conjecture called so-called periodicity conjecture. Yes. This conjecture is again due to Eldman and Skolonsky, and they claim or they conjecture that twisted periodic algebras must be periodic. Yes. Yeah. So this is their conjecture. But yes, yes, I should give some remark. Yes, the possible period is can be okay. Yes, period can be different. Namely, yes. So in the definition of twisted periodicity, here we have some automorphism. Yes. Then, yes, so this n can be different. So just by, yes, so assume that A is twisted periodic, then there exists some phi and n satisfying this isomorphism. But yes, we have to change this n. Yes, just to take some multiple of n, then this phi can be chosen to be identity. Yeah. So this is a meaning of periodicity conjecture. Yeah. It doesn't mean always this phi must be identity. Just changing n by possible multiple of it, we get usual or stronger periodicity. This is the meaning of their conjecture. Okay. So now, yes, let's explain, yes, how to construct or how to, yes, what kind of criterion we will give. Yes. Actually, the key notion of our result is given by so-called Calabi-Yau property or fractionally Calabi-Yau property. Let me explain this. Yes. So remember that, yes, assume that A is a finite dimensional K algebra, and assume that either A has a finite global dimension, or more generally, it is Gorenstein or Iwanaga-Gorenstein. Yes, in the sense that the injective dimension of A is finite over itself. Then it is well known that the perfect derived category of A, okay, this is just bounded homotopy category of finitely generated projective M. So this category, triangulated category, has a cell functor. Yes. Well, this is Auslander, essentially Auslander item duality for perfect derived category. And this cell functor is given by Nakayama functor. It is just a derived tensor product of taking derived tensor product with A bimodule dA. D is K dual A, as before. Yes. And using this Nakayama or cell functor, we can define fractionally Calabi-Yau algebra as follows. So now I start with take two pair of integer L and M, and I assume that L is a positive integer. Yes. In this case, we call our algebra A ML Calabi-Yau, or just L over M Calabi-Yau for short, if the following condition is satisfied. Yes. The condition is very simple. Just L's power of cell functor is isomorphic to the M's suspension functor as just ordinal functor on perfect derived. Yeah. Both are auto functor of auto equivalence of perfect derived category, and they are isomorphic. So this case we call A as L over M Calabi-Yau. Yeah. Yes. We cannot take common. We cannot factor out common factor of L and M. So this is a very dangerous notation. Yes. Often more carefully we call ML Calabi-Yau. Yes. And in this case, we just call A to be fractionally Calabi-Yau. Okay, maybe I should write fractionally Calabi-Yau here. Okay, maybe fractionally Calabi-Yau. Yeah. Or just F Calabi-Yau for simplicity. Okay, yes. And yes, yeah. When necessary, I denote by Calabi-Yau dimension of A to be the pair M and L if L is minimal possible. Yes. Yeah, as before, when we defined periodicity. And as in the case of periodicity, we also need a twisted version of this fractionally Calabi-Yau property. And the twisted version is defined as usual, or as before, by using K-algebra automorphism of A. Yes. And instead of, just this isomorphism, we assume that L's power of L is isomorphic to the composition of M's suspension factor and the induced automorphism of per A given by our automorphism phi. So this is a definition of a twisted fractionally Calabi-Yau property. Yes. Yes. So let me give the simple main example. Or yes, actually there really a lot of yes maybe I
Sorry, could I ask a question?
Yes.
For the twisted one, the minimality is depends on phi or not depends on
Twisted
phi.
case, I don't define Calabi-Yau dimension because it gets more complicated. Yes, I don't.
Okay, thank you.
One can of course define, but I don't want to do. Yes.
Okay.
So now, yes, maybe one remark is that so A is so if we have a finite dimensional Gorenstein algebra, then it is symmetric if and only if it is 1 over 0 Calabi-Yau. Yes. And yes, similarly, yes, we need yes, yes, and also A is self-injective if and only if it is twisted 1 over 0 Calabi-Yau. Yes. So, okay. Yes, I'm sorry. Yes. Yes. Assume that A is, yes, under the assumption, there is a bit something subtle. So, under the assumption that A is basic, A is self-injective, if and only if it is twisted 1 over 0 Calabi-Yau. Yeah. So in this sense, yes, so zero Calabi-Yau property is nothing but, yes, our well-known notion of self-injectivity or symmetry. Yeah. And yes, self-injective case, this twisting automorphism is just Nakayama automorphism of, yes, this equivalence isomorphism tells us that self-injective case phi must be just Nakayama automorphism of A for self-injective case. Also, there is another well-known class. It is just path algebra of Dinkin quiver. So if Q is the Dinkin quiver, then actually path algebra is fractionally Calabi-Yau. Actually, Calabi-Yau dimension is again given by Coxeter number, namely, yes, it is either half of Coxeter number minus 1 and half of Coxeter number or twice of this fraction. Yes. And these two cases are divided by the property that canonical involution is identity or not, as usual. So, yes, Dinkin quiver is fractionally Calabi-Yau. This observation is, I think, due to Yektieri, Miyachi Yektieri. And yes. And yes, there is also more example. For example, canonical algebra of tubular type are also fractionally Calabi-Yau. And there is also easy construction, inductive construction of fractionally Calabi-Yau algebra. Yes, actually, fractionally Calabi-Yau algebras are closed and taking tensor product. Yeah. So tensor products of fractionally Calabi-Yau algebras are again fractionally Calabi-Yau. And also fractionally Calabi-Yau algebras are also closed under derived equivalences. Yes, because yes, cell functor are derived invariant. Yes. So these are, yes, so taking, yes, these are easy, very easy, but observed in my joint work with Martin Helschent and myself. Yes. And actually, in a joint work with Martin, we pose a question. And let me state here as conjecture, well, to make compare with periodicity conjecture. Namely, the question is very natural. Assume that algebra A has finite global dimension. Then, twisted fractionally Calabi-Yau property is equivalent to fractionally Calabi-Yau property. Yes. Yeah. So this is a very natural, naive question. There's no counterexample. No. Yes. Under this assumption of regularity, finiteness of global dimension. Yes. Remark that yes, this conjecture or question fails if we drop finiteness of global dimension. Yes. Yeah, for example, there are many self-injective algebra whose Iyama automorphism has infinite order in outer automorphism. So such self-injective algebra gives obvious counterexample to this question. So yes, if we drop this condition, yes, this conjecture fails. Okay, so now it is time to state our result. So theorem 1, yes, assume that lambda, okay, A is a finite dimensional K algebra. For simplicity, as before, I assume K is algebraically closed. And yes, actually, this is, as I said, this is a bit strong. More generally, if you don't like so much algebraically closed field, it is enough to assume that A over radical A is a separable K algebra. Separability is often enough. Yes, this is a minor remark. Then our main result, yes, actually this first part is the main result. So claiming that characterizing periodicity of trivial extension algebra of A. Actually, periodicity of trivial extension is equivalent to that A is fractionally Calabi-Yau. Yes. And moreover, assume that finite global dimension. Yes. So remember that, yes, fractionally Calabi-Yau property is defined for Gorenstein algebra because we need a cell functor. But yes, yes, not just Gorenstein property, we need a regularity. So regular together with fractionally Calabi-Yau, this is necessary and sufficient for TA, trivial extension, to be periodic. And the second main result is a twisted version of this result. So trivial extension algebra is a twisted periodic if and only if is a twisted fractionally Calabi-Yau. Just twisted fractionally Calabi-Yau of finite global dimension. So just attaching twisted on both sides to first statement, we get equivalence. Yeah. And actually, twisted case, there are more equivalent condition we proved. And yes, other condition looks probably different from these two conditions. So let me state. So the third equivalent condition is that any module, finitely generated module of a trivial extension, has complexity at most one. Complexity at most one. So complexity just is just growth of terms of minimal projective resolution. So complexity at most one means the dimension of terms appearing in minimal projective resolution of X is bounded. So this is boundedness of projective resolution of X. Yeah. So periodicity is definitely stronger, or yeah, twisted periodicity immediately implies complexity at most 1 because this is numerical criterion. But yes, this is actually equivalent to twisted periodicity. And the third condition is also, yes, looks also quite different, but let me state. So there exists some positive integer R and G such that the R-folded trivial extension algebra of A. What is this? It is, well, roughly, yes, immediate, yes, easy definition is consider matrix algebra of this form. So, yes, diagonal entry are A and upper diagonal, first upper diagonal entry is K dual of A. This has a natural K algebra structure, yes, and this is R times R matrix. And this is actually covering, so-called classical covering in the sense of Gabriel of trivial extension algebra. And this has a D cluster tilting module. Yes. I don't have time to define cluster tilting module, but yes, it is important notion in higher dimensional Alcelander like this. Yes. And also appearing in cluster tilting theory related to categorification of clusters. Yeah. Anyway, yeah. So we have, so last condition looks rather different from others, but this is also equivalent. Yeah. So in the last 8 minutes, I explain ideas of proof and some example using our theorem. So, yes. So actually, first property, proof of first property is much more harder than second one. Both actually use singularity category of M. Yes. So key role is played by the singularity category of trivial extension algebra and its graded version. Yes. And remember that, okay, I use this symbol for singularity category. And remember that the singularity category is nothing but the stable category of our algebra. Yes, Gorenstein has. And similarly, G-graded version. Yes. So this category plays the central. And under the assumption that, yes, now under the assumption that global dimension of A is finite. Yes, there is a very well-known equivalence due to Hopper. Yes. Somehow, yes, starting point of first on the both first and the second condition statement is triangle equivalence between bounded derived category of A and the singularity category of trivial extension algebra. Yes. So this equivalence, this triangle equivalence is actually the starting point of both statements. And periodicity is both twisted and usual periodicity is the property of this stable category. But it has natural covering, or well, this is not dense, so pre-covering. And actually the point is that cell factor of the stable category of trivial extension is given by composition of inverse suspension factor and degree shift factor. Yes. So this looks a bit strange, but this is just an inverse suspension factor. And this is a category of graded module. So we have a natural degree shift factor. And this is actually by classical Auslander-Leiten duality. This gives a cell factor of this triangulated category. Therefore, yes, classical Nakayama factor is nothing but this factor. Yes. And therefore, yes, so fractionally Calabi-Yau property is basically periodicity of nu up to certain shift factor. Yes. Therefore, yes, and also, yes, periodicity of syzygy. Yes, one important point is, so yes, we can write down this as omega with degree shift factor. Yes. Yes, because -1 suspension factor is nothing but Syzygy factor. Therefore, we have some commutative diagram like this. Yes. So degree shift factor is trivial here. So we have a commutative square consisting of Syzygy factor, endomorphism of here given by Syzygy, and automorphism of this given by Syzygy, and automorphism of this given by this composition. Yes. So this is an idea. Yes. So fractionally Calabi-Yau property is basically periodicity of new modulo suspension factor, and yes, therefore it is yes very close to periodicity of Syzygy factor. So this is an idea. Yes, and one can justify this idea to prove this equivalence. Yes. So this is yes two-line proof of our theorem. Yes. And yes, I have last 4 minutes, and yes, actually, second condition is actually much harder to prove, and maybe just yes, let me explain some key ingredient of proof of first part. Proof of first part. So yes, to prove yes, idea of or ingredient of proof of one is we use we use DG algebra corresponding to trivial extension algebra. Yes. And we take a bimodule resolution. So using AE projective resolution of dA. Yes. So we define new differential graded algebra. So let me write down P as resolution of dA as enveloping algebra of A. We define new differential graded algebra C as trivial extension of A and P. Yes. Then this algebra is derived equivalent to trivial extension algebra, but actually this algebra is actually necessary to prove first state. And we use singularity category of enveloping algebra of C, which is equivalent to singularity category of trivial enveloping algebra of trivial extension algebra of A. And yes, and we calculate A and yes, nth Syzygy of A in this category. Yeah. So this is very yes. And yes, we calculate Syzygy in this category. So this is a two-line proof of our theorem, part one. Yes. Okay. So yes, because yes, I think I still have 2 minutes. So let me give some example. And yes, or maybe yes, yes. Let me tell you some corollary. Yes. And actually, first corollary is that, yes, two conjecture. We state two conjecture. First conjecture is periodicity conjecture. Yes, twisted periodicity is equivalent to periodicity. Another conjecture is fractionally Calabi-Yau conjecture. So twisted fractionally Calabi-Yau conjecture. Twisted fractionally Calabi-Yau property is equivalent to fractionally Calabi-Yau property. And one of the conclusion is periodicity conjecture for trivial extension algebra is equivalent to that fractionally Calabi-Yau conjecture itself. Yes. Yes, this is because, yes, thanks to this equivalence. Yes. So both periodicity and twisted periodicity are equivalent to fractionally Calabi-Yau or its twisted version. So equivalence here is equivalent to equivalence here. Yeah. So this is also quick proof of this. And another conclusion of our main result is that if outer automorphism group of A has finite order, then periodicity conjecture holds for trivial extension algebra of A. Yes. So if trivial extension algebra is twisted periodic, then it must be periodic. Yeah. Yes. And yes, we can apply this second part. We can prove, for example, the following. So if we have a finite lattice, yes, so this is a poset with join and meets, and then we can consider the incidence algebra of this lattice. Yes, incidence. Then one can easily check that outer automorphism group of incidence algebra of lattice is always finite. Therefore, periodicity conjecture holds true for trivial extension algebra of such incidence algebra. Yes. And another corollary is that, yes, twisted fractionally Calabi-Yau algebra of finite global dimension, yes, they are closed under derived equivalence. We already state that just fractionally Calabi-Yau algebra of closed under derived equivalence. But if we, but twisted version are not just question in my paper with Martin Herschend, but using our second result for twisted periodicity, we can give positive answer to that question. Yes. And there is many algebra we can, we can prove many algebra to be fractionally Calabi-Yau or twisted fractionally Calabi-Yau or periodic or twisted periodic by using ours. But my time is now over, so let me finish my talk. So thank you very much for your attention.
Thank you, Osamu, for your nice talk. It was a very wonderful talk. If there is some question, please ask. Also.
Yes, I would like to ask the final
Yes, please.
corollary. Yeah. So as before you said that if without twisted, then it is closed under derived equivalence, but without the condition finite global dimension. But here need this condition.
Oh yes, your question is if we can drop finiteness of global dimension. It's very likely, yes, to drop, yes. But at least our approach, our proof require this technical assumption of finite global dimension. Yeah. So yes, this should be one should be able to drop this condition too, I think. Yeah, I think.
No, I mean drop the second condition. Yeah, finite global dimension.
Yeah, sorry. Yes, I mean this. Yes, sorry.
Oh, okay.
Yes.
So if we drop this, no counter example so far.
Yes, no counter example. Yes.
Okay, thank you.
Yeah, because our automorphism group is not derived invariant information. So outer automorphism group appear in this definition, but it is not derived equivalent. So this is somehow difficulty. So fractionally Calabi-Yau property is obviously derived invariant property, but its twisted version is a bit subtle. Yeah.
Okay, thank you.
Automorphism group is not invariant.
But I think it behaves well on the stable equivalence. How about stable equivalence? Because the definition is based on the stable category. Is it close under stable equivalence?
About the fact. Sorry. You are discussing.
Yes. How about the periodicity? Yeah. How about yes? Is it close under stable equivalence? Or I mean, the first one.
Yes.
Yes.
You mean this one? Or
yes, periodicity. Yes, periodicity is close under stable equivalences because periodicity.
Periodicity. So yes.
Yes, exactly. This one, periodic algebra.
Yes, let me state first. Yes, so periodicity is a derived invariant property. Yes.
Yes.
This is okay. Yes. Yes. Periodicity is derived invariant. But what about the twisted periodicity? I'm afraid I don't think so much, or at least I don't remember right now. Twisted periodicity, yes, thanks to this equivalence, it is a derived invariant. Yes. Twisted periodicity is a derived invariant property. Yes. But yes, this n can be different. Yeah. Period can be different,
But I'm asking, how about under a stable equivalence? I mean, this property.
Periodicity. Yes. First property is
definition under
first
stable.
property is yes preserved by stable equivalence. This is exactly the reason derived equivalence preserves twisted periodicity.
Yes. Yes, thank you.
Derived equivalence implies stable equivalence, and stable equivalence preserved this property. Finiteness order of suspension or Shizigi factor. Thank you very much for pointing out all this.
Always derived equivalence implies the stable equivalence when the algebra is self-injective.
Well, this is true. Yes.
Are there any more questions? There are, so let's ask. Seems there are, but